5.3 exponential models. So we're going to take a look at the growth of bacteria. Okay, when some foods, such as fresh meat, are left at room temperature, any bacteria in the food will begin to multiply. If enough bacteria are present, you can become ill from eating the food. This is known as food poisoning. The most common bacteria found in food are Salmonella and E. coli. Okay, the graph shows the growth of an E. coli bacteria population over time. Okay, so describe the relationship between the number of bacteria and time. So if we take a look, what's time? Time is going to be on our our x-axis, and then number of bacteria is going to be on our y-axis. And we always read graphs going to the right. So if we read the graph going this way, we can say that as time increases, the number of bacteria increases. I'm actually just going to put that upward arrow. Okay, use the graph to estimate the number of bacteria after each time period. Okay, so after 20 minutes. Okay, so at 20 minutes, we're going to be right here. We followed up to the graph and followed over. I'm going to say about 18. Bacteria. Okay, 40 minutes, so we're going to go 40. We're going to follow it up to the graph. As soon as we hit the graph, we're going to follow it over. I would say it's about 40, maybe even 39. Okay, so 39 bacteria. And then at 60 minutes, so right at an hour, okay, I'm going to say 76. Because I can see that I'm like going up a little bit, but it's more across. Okay, BAC like bacteria. Okay, so now what we're going to do is we're going to calculate the ratios. So we're going to go 39 over 18, and we get 2.167. And we're going to put 76 over 39, and we're going to get 1.948. Okay, so if we take a look at the ratios between these numbers here, we get approximately 2. Approx 2. Okay, so what happens to the number of bacteria every 20 minutes, right? Because we did 20, 40, and then 60, right? 18, 39, 76. What happens to the number? It approximately doubles, okay? Approximately doubles. Okay, consider the rate of change of the number of bacteria with respect to time. What suitable units for the rate of change? So going up here, we would say number of bacteria over minutes. Okay, so number of bacteria per minute. Bacteria per minute. Okay, and remember that's always delta y over delta x. We always want to state this y, this dependent variable over the independent variable. Okay, and F is the rate of change of the number of bacteria with respect to time, increasing, constant, or decreasing. Okay, this is definitely increasing. Okay, we took the ratios and we saw that it doubles. And this is definitely nonlinear, so it's not constant. And because it approximately doubles, what we actually call this is exponential. Okay, example 2, smoke detectors. So, Americium 241, so AM241, this is a manufactured element and it's used in smoke detectors. So household smoke detectors have approximately 200 micrograms of AM241, and this amount decays over time. So if you actually pick up your smoke detector, it has an expiry date on the back of it, okay? Because it decays over time. It starts with 200, just as an example. The table below shows the amount of AM241 remaining in micrograms over 1,000 years. Okay, so let's calculate the first differences. So we actually go up this y column. So we're going to go 40 minus 47, negative 7. 47 minus 55, negative 8. Okay, 55 minus 65, negative 10. And you keep going up. So I'm going to go, this is negative 11, negative 14, negative 15, negative 19, negative 21, negative 25, and negative 30. Okay, remember first differences will not have a value here. Second differences will not have a value for 2. Now second differences, we take the difference of the first differences. So I'll show you 3 of them, or 2 of them even. There we go. Okay, so negative 7 minus negative 8. Okay, which turns into positive, so that's just 1. Now negative 8 minus negative 10, remember the double negative turns into positive, so we get 2. Okay, and if you keep going up, we get 1, 3, 1, 4, 2, 3, 5. 4, 2, 3, 5. Okay, so what are the ratios? Sorry, going back, first differences are not constant. So we try the second differences, those are not constant. Now we calculate the ratios. So what we can do here is we go back to the y column and let's actually divide. So we're going to go 40 divided by 47. We get 0.85. 47 divided by 55. We get 0.85. Okay, 55 divided by 65. 0.85. Okay, and if we keep going, we are going to get 0.85 for this entire column. Okay, and then these are obviously rounded. If you take a look at your calculator, it has many, many, many decimals. So these are rounded, and that's okay. Okay, A, does the years column show equal time intervals? Yes, it shows everything going up by 200, okay? Yes, increases by 200 each time. Okay, calculate the first differences, done, second differences, done, and ratios. Is a relationship between mass remaining and time linear, quadratic, or exponential? Okay, so as we can see, this ratio column is constant, so this is definitely going to be exponential. Okay, BC, because the ratios of the y's are constant. Okay, so what I'm going to do is I'm going to actually graph this, and I'm going to put AM 241 remaining. Okay, so up the y-axis is going to be mass remaining, and across the x-axis is going to be year. Okay, years passed. Okay, so it starts at 200, and then it goes down to 170, and then it goes down to 145, 124, 105, 90, 105, 90, 76, 65, 76, 65. Oh, here. 55, 47, 40. Okay, so it starts at 200, and we can connect these with a curve. Okay, we can see that that's not a line. That's definitely a curve. And this is supposed to say C. Compare the table and the graph. Does the rate of change of mass remaining with respect to the year appear to be constant, increasing, or decreasing? Okay, definitely decreasing. Okay, because it's more gradual. Okay, so it's not constant, so it's not a line. It's more gradual. Okay, and then like it tapers off. And that's how an exponential function looks. Okay, it's steep at first, and then it starts veering off as it approaches a certain number.